Okay, we're going to get going. There's still some more people coming in, but they'll file in as they need to. My name is Adam Greco, and I work for Search Discovery. Thank you so much for joining another one of our SDEC sessions. For those of you who are new to the SDEC, our goal is to provide free education as a community to anyone who really wants it around digital analytics, and we have about 12 different topics that we cover. Today, we're going to be talking about the testing topic. So if you want to learn more about other topics, you can join, or if when you originally signed up, you didn't join all the topics that you wanted to, feel free to email sdec@searchdiscovery.com and I can verify with you which topics you are signed up. This will be recorded, so if there's anything you want to catch up on, it will be posted later in the SDEC Slack group. And if you're listening to this webinar and you're not already in the SDEC Slack group, that Slack group is becoming more and more important as our group grows. So I would highly encourage you to join that group. And again, if for any reason you have any troubles joining, just email me at sdec@searchdiscovery.com. As we go through this webinar, if you have any technical problems or issues, feel free to use the chat that is available in Zoom. But if you have a question for Merritt, please go ahead and use the Q&A area because the ones in chat don't actually funnel through the right way, and we will get to questions afterwards. So once again, thank you for joining, and Merritt, I will hand it off to you.
Thanks, Adam. So my name is Merritt Aho. I am an optimization director at Search Discovery. I've been working in the optimization, online A/B testing, and experimentation space for about 9 years or so. And what we're going to be discussing today is a labor of love for me. It's a tool that I wish someone had handed me, gosh, 6, 7 years ago. Anyways, I've been with Search Discovery about 1.5 years. Among other things, I'm known here for sharing bad jokes with people, dad jokes. So I'm going to start there because I have a captive audience and y'all can't stop me. So just a quick question. What do you call a bomb that lands on a cow and doesn't explode? So I would call that a milk dud. And if you were groaning right now, that was the point. Anyways, so we're going to dive right in here. This is a calculator that we built that is available on the Search Discovery website. And you can get a quick look at the calculator here on the right, but I'm going to spend a lot of time going through the deck because if you start from zero and dive right in, it can be a little bit overwhelming. And so I want to control the exposure of information here to be able to explain it fully. But feel free at the same time to be on the website playing around with the calculator. And we'll start with a little bit of theory behind why this calculator exists. So to understand this sequential testing calculator, you need to first understand what fixed horizon testing is and what peaking is in regard to fixed horizon. So you may have done a lot of experimentation and not heard the term fixed horizon. However, you've probably done it. Fixed horizon testing is where we start with a power analysis, or we're determining sample size given a number of test parameters to control our error rates. Type 1 error rate is false positive, type 2 error rate is false negative, and we're controlling that around a certain sensitivity of our test. And in a fixed horizon test, you set your sample size and you are supposed to test until that sample size and not stop until you get there. And that's law. That's scripture for A/B testers, and that's what we know. And peaking, of course, is the violation of that test law. That's when you are checking your results early with the potential or intent to stop the test based on early results. So the problem with peaking is that it increases your type 1 error rate, increases the rate at which you get a false positives. And so suddenly you go from a very controlled environment of testing to a very uncontrolled environment of testing. We'll get to that in a second of how exactly that impacts you. But there are some pretty good reasons why people peak or why they would want to peak. I mean, first of all, like the cost of running a test is in part the time that it takes to run that test. So you may have other tests that are queued up behind it. and getting to those tests means you can do more with your time. Also, you know, when the results start coming in on a test, ending it early could potentially limit the exposure of a bad experience. If it's a really good experience, a powerful change, it could monetize the value of that change. And I don't know what kind of organization you work in, but in a lot of the organizations that I've worked with, stakeholders who are not as familiar with A/B testing, don't care about type 1 or type 2 errors, and just want to know if something works better, are very eager to make a decision and move on to the next thing, especially when the data looks compelling. Of course, as we know, that it's the fact that the data may look a certain way to us, that's the reason we have statistics, because our intuitions are not always that great. So there are good reasons to peak. The problem is that it results in some bad stuff. So what you were seeing in this chart is simulated data. And what we're looking at is if we peak at our test when there is actually no difference in between the test and control. So the null hypothesis in this case is true. There's zero effect size. When we peak every 10% of our sample being collected and run a test on it, what this is showing is at each increment, how many additional tests are going to give us false positives. Now, the first time we peak at 10% of our tests, we get 10% false positives. And that's with, this is with a 90% confidence level, right? So at 90% confidence level, you should expect 10% false positives. And what do you know? The first time you check at 10% of the sample, you get 10% false positives. Problem is, if you check again at 20%, you get an additional 5% false positives, drops to 3, 3, 2, 2. In total, right, if you were to stop each of those tests after you reached confidence, you would have stopped 30% of those flat tests for false positives, right? So your type 1 error rate went from 10% to 30% just by peaking. So this is the problem with peaking. This is the challenge with fixed horizon testing. And so what the sequential test calculator does is it utilizes a sequential testing method. There are multiple sequential testing methods and many different approaches to utilizing those methods. But this uses one to allow you to peak responsibly while controlling your error rates. So the main stages of this, and by the way, this calculator is not just for planning your test, it is planning your test, but it's also for analyzing your test and producing some results. So 3 main phases here. It starts basically like any other A/B test that is a frequentist test with your parameters of significance level, of power, of minimum detectable effect, or minimum effective interest, whichever you prefer to call that. And then you need to plan how frequently you are going to check in on the test results and the frequency of those check-ins. And then you need to calculate what's called decision boundaries and a maximum sample size. And we'll get to that in a second. But then during the test, you're really just realigning that test plan with what actually happens, because sometimes it's hard to anticipate exactly when your check-in is going to occur. And you are looking at z-scores during the test. And we'll talk about why z-scores as opposed to p-values, which you're probably used to seeing in tests, or even confidence levels, which you're probably used to seeing as well. But you're taking that z-score, you're comparing it to a decision boundary, and you're either stopping or continuing the test. And then after the test, just like in a normal test, you would report back your confidence level. You know, this reached 98% confidence or 99% confidence, and a confidence interval, which is the range in which you would expect the effect size or the true difference to actually be. And those come out adjusted based on the sequential methods. So if you do not adjust those, you get bias in those effect estimates. And so those do get adjusted. Okay, so that's like the order of operations in doing a test like this. But I do want to say that this entire calculator, before we get into it, is based on an R package. It's a Shiny app, so it's based in an R package called GS Design. And that is a very powerful R package. It allows you to plan and execute sequential tests using a variety of approaches. and it's really worth checking out. So not to downplay the calculator that we're going into, but you could create something like this on your own with that package. And I should say, at Search Discovery, our goal is to develop the knowledge of our clients and to help them kind of figure out how to do this stuff themselves. And so that's, we try to be very open about what's behind this. And I'm more than happy, if you have any questions after this, to reach out, or if you are interested in recreating something like this on your own, be happy to help you in any way I can. Okay, so let's dive in to the calculator here. Okay, like I said, it starts out like any other test. Step one, you got to put in your confidence level that you want, the power that you want. So confidence corresponds to alpha, power, beta, or type 1 error rate, type 2 error rates. And then base conversion rate, whatever you're starting with of your test audience. Minimum effective interest, or your MDE, again, that's the sensitivity of your test. And in the calculator itself, you can use these little icons over here, click on them to expand to get a little bit of explanation about what these are. And then tails, you can select a 1 tail or a 2 tail. The one thing I'll say about that is even a 1 tail experience, you will get what's called a futility boundary. So you'll get a lower boundary that you're comparing your results against to determine if you can end the test early if it's not looking like a winner is likely. Okay, so from there, step 2, here's the bad news. You do have to do a little bit of additional planning when you're doing a sequential test. I know it's probably tempting to want to think like, I really just want to like run my test and check the results and then, check them as often and frequently as I want to and have that control my errors. This doesn't work like that. Just like in a normal A/B test where you need to plan for sample size, you need to do some planning ahead and say, okay, I'm going to check in on the test every couple of days. The test is estimated to run for 3 weeks, and so that's going to be 6 or 7 check-ins. And so you need to plan those number of check-ins. Those are going to determine where the decision boundaries align, and it's also going to determine what the maximum sample size is. So in this sequential testing method, we don't just go until we reach confidence. That's not a thing here. We are planning to a maximum sample size. We are planning around a specific power level, to a specific sensitivity. Okay, so what you're doing is you're saying, I'm going to have X number of check-ins. We're allowing you up to 10. And then you can select at which percentage of the sample you're going to check in on the test. So you may, for instance, want to check in on the test really early on. So you may select like, I'm going to check in at 5%. And then after that, I'm going to wait a while. I'm going to check in at 40%, 60, 80, and 100. Of course, you don't need to put in the 100% one here. It's assumed, but you need to program in the other checks. Then you just hit View My Design, which is a little CTA there, and you're going to get spit out the design of your test. Now, the first thing you're going to see is that under a normal fixed horizon test, it's going to show you what the sample size would be, and it's going to show you the maximum sample size for a sequential test under this design. Now, the more number of checks that you program in, and the more dispersed those checks are, the greater the total increase in sample size is going to be. You can see here with 4 checks spaced every 25%, it's about a 10% maximum increase in sample size. Now, on average, your tests are going to run much shorter. And I've got some data I can share on that in just a second here. But in this case, the maximum sample size, if you're not able to make a decision early, will be 10% higher. Okay, and you get this table. And this table is showing you, it's projecting out your tests. So it's saying like at each of those inflection points where you're going to do an analysis on your test, 25%, 50%, this is what the sample size is going to look like. If you utilize, there's an input there in the first step to put in your average weekly traffic to the test area. And so if you put that in, it'll estimate the number of days it'll take you to reach one of those checkpoints. And then you get, this is the crux of it here, the lower z-score and the upper z-score. These are your decision boundaries. And we go ahead and we plot these out for you as well. But you may be wondering, why are we looking at a z-score and what the heck is this z-score? So hopefully you're somewhat familiar with the concept of a normal distribution and the central limit theorem in hypothesis testing. What a z-score tells you is it's roughly equivalent to the number of standard deviations away from the mean that a specific observation is. So there's a lot in this chart here, by the way. It's probably maybe a bad judgment of mine to put it in here and not explain it all, but there's some really good information here. And what I wanted you to see was a z-score roughly equates to standard deviations from the mean. And it also relates heavily to the confidence levels that you get. You'll see like cumulative percentage down here below, that would be like under a one-tailed environment. And then you'll see it depicted here as more of like a two-tail, the number of standard deviations away from the mean that an observation is. For example, a z-score of 2 will be roughly equivalent to like a 95% confidence level with a two-tail. So why a z-score? Well, here is a Excel formula that computes a p-value from a z-score. And in fact, all p-values are derived from z-scores. A p-value, though, I have a theory about why in all the literature you read on sequential testing, they're all talking about z-scores and not p-values. I think that's probably because p-value means something specifically, right? You take 1 minus the p-value and there you have your confidence level. Well, hopefully you've caught on by now that the confidence level that you would get from a normal calculation here is not the normal confidence level, or it doesn't mean the same thing, right? It's supposed to tell you something about the false positive rate in your data under the null hypothesis. But when you're peeking at the data, when you're doing that sequential testing, that confidence level is actually inflated. And so like the false positive rate is actually much higher when you're checking multiple times. So I think the z-score, I mean, for one, it's not necessary to calculate the p-value to use z-scores in this type of analysis, but also I think it's a little bit easier to keep you from making interpretations about false positive rates at that point. Okay, so I mentioned the boundaries. We have plotted those for you in the design outputs. And you get an upper boundary here and a lower boundary here. And basically what you do as you go through the test is you calculate a z-score and you compare it to these boundaries. And if you're within the boundaries, if you're lower than the upper one and higher than the lower one, you continue the test. You have inconclusive results at that point. But if you cross a boundary, that's when you can end the test early. So there's a name for each of these boundaries. Under a one tail at least, we call this the efficacy boundary. This is if you're doing what we call a superiority test, or if you're testing for B being better than A, or for your test group being, performing at a higher level than your control group. The futility boundary would be the point at which you give up on something. Now, what you will notice here is that these scores on the futility boundary, they start negative, which you could infer that's representing a decline in conversion rate or in your metric. But then it actually moves into the positive range, which means when you cross a futility boundary, let's say you could have a z-score of 0.8 at the third check-in here, that represents a positive, like an actual increase in conversion rate, but you're giving up on it. You cross your futility boundary because it's not likely to cross the efficacy boundary. You also notice that these two boundaries converge at the end. And that is because at the end of the test, when you've reached your maximum sample size, you're either going to hit significance or you're not. All right, there's no being between the decision boundary at that point. You either determine that you've reached significance and you've got a winner on your hands, or it's an inconclusive result. Okay, so this is what it looks like for a one-tailed test. You'll notice that these boundaries are different from each other. Under a two-tailed test, which you can also run, the boundaries are identical. And they're also wider, right? So these are based on the same underlying data, but one tail to two tail, you go from 3.16 to 3.36 for that first check-in, 1.71 to 2.03 for the last check-in. Okay, so that's the design of the test. Now let's talk about how you analyze a test when you're going through. Because we do have this last sort of component to the calculator that is an analysis component. And so what you have here is these are actually tabs. You have a tab for each of the check-ins that you have planned. And what you do is you click on the appropriate corresponding check-in and put in your results. So currently we only support conversion rates with this data. Hopefully in some future version of the calculator we'll support continuous metrics or metrics like RPV or time on site or page views per visitor, you know, something like that, right? Again, right now we only have binomial metrics. So it's got to be a rate or proportion. So you would put in the traffic in your control, the conversions control, traffic test, conversion test. Immediately what spits out here is a calculation for that data. It tells you your rates. It tells you the relative difference in those rates. It gives you a z-score, and it spits out the percent sampled. And this is important. We'll get to that in just a second. But you basically go in and put in the data for the corresponding checkpoint. And it is important that you put in the right data for the right checkpoint, because that is the z-score, the boundary level that's going to be compared to your z-score to determine the results. So you would do that for checkpoint 1, you can do it for checkpoint 2, and then you can plot your results. And so those results will show up. That's the blue line here under the decision boundary plot. Now, the unfortunate thing, again, this being a Shiny app, we do not have a save function here for your data. So I recommend you take a screenshot of your data as you put in, so you can kind of come back to it later if you need to, if you haven't finished the test yet. Now, this should bother you, and not just because you're OCD. You may be like me and you just want things to line up perfectly, but the problem here is the data that I have put in here does not correspond to the sample size that I had planned for my check-in. And this can be a problem if your boundaries are not, if the z-scores are close in one way or the other, and the boundaries are not lined up perfectly, then you might actually get the wrong results. So it's very easy to correct this. All you do is you go back to the design point, you take that percent sampled that was spit out in the checkpoint calculation, and you put that number back into the design. So I think before it was like 25%, 50%, 75%. We reset that to 24%, 39%, 75%. And then if you click calculate, click calculate, it will line up those boundaries perfectly for you. You'll notice that you got a different value here for the boundary. 2.52 is the original, 2.8. And this is acceptable practice. I know a lot of times in fixed horizon testing, we get the mentality that like we can't change anything in the test. Like once we've set it, once we've designed it, it's set in stone. We don't change it. We don't go back. That'd be p-hacking. This particular practice is acceptable, right? All you're doing is you're identifying a different point in your decision boundary, and you're sort of reworking that to match the actual point for your analysis. Now, when you cross a decision boundary, if it is an efficacy boundary or if it's a two-tail and you cross the lower boundary, you do get a confidence level and confidence interval output. Now these, as I mentioned at the beginning, these are adjusted. And so if you were to go and run this same data through a normal confidence calculator that you would find on the internet, they're out there in abundance, or calculate your own, they would not come out to the same. In fact, your confidence level would typically come out to be a little higher and your confidence interval would come out to be a little tighter. Now those need to be adjusted. They cannot be relied on perfectly. There's bias that gets entered into those estimates. And I should say they're varying, not all of these biased estimates are created equally. And I would be remiss if I didn't mention that, Georgi Georgiev, who runs analyticstoolkit.com, also has a sequential testing calculator out there available. You do have to pay for it, but it's a very reasonable fee. And he actually has some even more advanced estimates and bias. He has some more advanced ways to remove bias from these calculations. And so his are even more conservative than these and worth checking out. The other concept that comes into play here is the concept of a binding versus a non-binding boundary. So a binding boundary means when you cross it, you need to stop the test. And the assumptions, the statistical assumptions that are made here are contingent on you stopping the test when you reach that point. A non-binding boundary means you can cross the boundary, but you don't have to stop it. You can just consider it interesting and you can go to the end of the test. It doesn't mean you continue past the end of your planned sample size. That's a no-no still. But you can, so the futility boundary in a one-tail test here is a non-binding boundary. The efficacy boundary is a binding boundary when it's one tail. In a two-tail test, both of those boundaries are binding. And that is documented in the calculator as well, so you don't have to go without it. So I think we've gone through this stuff enough. Let's check out the calculator real quick for an example. And let's see here. So what you will see on our website is this page. And by the way, there's a video, there's an article and a video link to on this page that kind of gives you a walks you through some of the methodology here. So this is what it will look like to you. I'm going to just go ahead and run this out of the R session, and it'll just be a little bit cleaner for us. So there are default values that are put into here. Basically the ones I had screenshotted there, 95%. But you can, let's say you want to switch these around. You want to use 90% confidence and 85% power. And your base conversion rate, let's say it's 5% instead of 10%. In your MDE, sure, 10% looks good. Actually, let's put it down to like 8%. So what you'll notice here is I mentioned you have the opportunity to put in your average traffic to the test page or test area. And what you get spit out here is what the sample size would look like for a fixed horizon and the estimated duration of that test. Now, if a test is going to run for more than 14 days, this may be a great candidate for sequential testing. If it's going to run for fewer than 14 days, you might want to reconsider your strategy to do sequential testing in the first place. You want to always run tests for at least one, maybe two business cycles. Now, that may differ quite a bit based on the business. You also want to take any special events into account that might be happening during your test so that you get like a good sample. For example, if you run a test just over the weekend and your weekend audience performs a little bit differently than your weekday audience, that's maybe a bad practice, and you should consider running it for weekends and weekdays and maybe a couple of each. So this is really useful when you need to shorten the length of your test, but you don't want to shorten it too much, or you may get biased test results that aren't representative of how something would perform during every stage of your business cycle. So off my soapbox there. Then we're gonna plan the number of check-ins, and let's just say we move it up to 5. These spit out to even distributions, but again, let's say I wanted to check at 5%, and then I'll leave these other ones at their defaults. I can view my test design. That spits out below. And you'll see under this design, the maximum increase in sample size is 12.3%. The decimal is probably superfluous there. But you see the table that gets spit out here, our schedule of when we're doing check-ins, maybe 3 days, maybe 3 weeks in, 21 days, 32 days, 42 days. And you can adjust these again. You can say, instead of doing that, I'm gonna do 20% and 50%, and then I'll keep the one at 80%. And it'll spit out 3 days, 11 days, 27 days. We get our decision boundary here, and then let's go ahead and put in some test data and see what it looks like. So I'm just gonna kind of eyeball it here off of where the sample should be. So maybe like 1,300 in that guy, and 800. So it spits out our results immediately. We can see our z-score is 2 here. It's going to compare to the 4.21. We can plot that and see, okay, our boundary and our results are pretty closely lined up, so I'm not going to worry too much about adjusting it, although if I want to, again, this says our percent sampled is 3%. All I have to do up here is change this to 3%. Reswizzle that, and it lines it up exactly. Okay, so let's say we continue down the road. Our next check-in would be at about 15,000 total. So we'll go, let's go 8,000. And I'm just going off of like a 5% conversion rate, which is kind of what I put in there for the base conversion rate. Say 500. And I plot my results. And okay, these aren't lined up perfectly, so I'm going to make sure that I reset the boundary to 22% up here. And I've crossed a decision boundary. So I have very high confidence on this. It gives me the confidence interval. So it's saying that the difference in conversion rates, 95%, so it's based on my confidence level that I selected. It's going to fall between 2.6% and 47.5% increase in conversion rate. Okay, this is a binding boundary, so I do need to stop the test here. If I'd crossed the, in fact, if I just like reswizzle this, let's say I got 300. Well, that's really low. So let's say it was 350. Now, if I'd crossed the lower boundary, here in a one-tailed test, it's not going to give me confidence level and confidence interval on the lower boundary cross. But it is going to tell me I crossed, and it's up to me because this is a non-binding boundary whether I want to continue or stop the test. Now, I do preserve my power, right? My type 2 error rate, the chances of getting a false negative, given that the difference equal to my MDE does exist. I'm preserving that here, but I can keep going until the end of the test if I want to. So I just one more thing I want to say, and I'll wrap this up. And that is, what can you expect to get out of this? So just two quick charts here. One, with simulated data here, using this methodology, if I look at flat tests, right, that's like worst case scenario under the null hypothesis, a flat test where there's zero effect. What I'm seeing here with these test parameters, simulating 10,000 tests, roughly 56% of tests stop by the halfway point of the test. And an overall savings, even accounting for that 10% increase in sample size for this design, there's a 34% average time savings on these flat tests. So definitely more efficient to run this than the fixed horizon test. When there's a positive increase exactly equal to my MDE, I'm seeing about an 18% average time savings on tests. Now, the sequential testing method is really good for extreme results. MDEs are extremely difficult to estimate. Like, what is the actual difference going to be under this test treatment? We get that wrong almost always. And because it's so difficult, this can really provide value when that difference is much bigger or much smaller than you'd expect it. When the actual difference is somewhere between the null, which is going to be flattened superiority test, and your MDE, that's where the fixed horizon is much more efficient. But again, when there are more extreme results, that's when the sequential testing really can help you out here. So I will stop there and take any questions that may have come in.
Awesome. Thank you so much, Merritt. So if anyone out there has questions, we've got about 10 minutes to cover some questions. We already have a couple that have come in. But if you have any other questions, feel free to go ahead and post those now. So some of these questions aren't going to make as much sense to me as hopefully they do to you, Merritt. So you may want to just read them right now. There's one that actually came in, but Bruce had said that you may have already just answered his question, so maybe just kind of read his and see if there's anything you want to add to that, and then maybe check out Alberto's and maybe read the question aloud before you answer it.
Okay. So I think I did answer Bruce's. So Alberto's, about the analysis sampling, it is okay to adapt the sample size in the check-in setup. If I get you right, it is not changing the test setup, rather adjusting the sampling of the Z-score. Is it okay to adapt the sample size in the check-in setup?
It looks like he posted that both, I think you may have answered his question as well about evaluating the time saving.
Yep. Yeah. So you don't, and to be clear, you don't want to change, like I've gotten the question before, like, what if I'm close to the decision boundary and I get to the end of my test? Can I extend the test farther? We're getting to the outskirts of my understanding of what exactly happens there, but I view that as sort of a p-hacking scenario. It could be potentially possible to extend out the test, but it does create a multiple testing scenario, right? And so it does inflate your false positive error rate, and so you'd have to make adjustments to those estimates.
Cool. So if anyone else has any other questions, go ahead and post them. I think this session was a little more straightforward in terms of just using the calculator. So we'll hang on for one more minute. If not, we will let everyone go a couple minutes earlier.
While you're thinking of stuff to say,
actually, we just had some stuff. We did just have one come in. So Bruce had said, can you talk a little more about the trade-offs between using a one-tail versus two-tail test, and when we might use one versus the other?
Trade-offs between one-tail and two-tail. Well, so for one, a two-tail is a more expensive test in terms of sample size requirements. And a lot of people like to default to a two-tail test, but I think I actually think it goes back to your hypothesis. Is your hypothesis that that one is better than the other, that the test is better than the control, or is your hypothesis that there is a difference between the test and the control? So typically in A/B testing, my experience is that we're looking for an advantage, and so we will run a superiority test or a one-tail test, and so it's not actually necessary to do the two-tail. But if you really do want to know if the test experience is worse than the control, then you can run it as a two-tail, and you'll be able to estimate if there is a difference between them and not just if one is better than the other.
And then I think he had someone had said something about why again do you want this approach versus normal testing?
Well, if you don't want to take this approach, you certainly don't need to. What this does is it allows you to run more efficient tests in the face of extreme results. So if test duration, so for many of our clients and a lot of people out there, the cost of running a test is also measured in terms of the duration of a test. And so if a test is going to take 3, 4, 5, 6 weeks, that is considered a fairly expensive test to run. I mean, not just the resources that you may spend monitoring the test or managing the test or holding off on making any changes to the code base during the test, but also the opportunity cost of not making an early decision on that test, whether that be because the test is performing extraordinarily well and you want to monetize that, or performing terribly and you don't want to expose yourself to the risk of a bad performing test. And then we talked about, stakeholders who are often impatient about tests. So there are, the duration of the test is a cost of running the test. And so the advantage to sequential testing is that you can run shorter tests and still maintain the tight controls over your error rates.
Okay, so we got two more questions. How do you manage the continuous experiment sample size for sequential experiments since the sample size calculator is not available yet? Not sure if I get that one, but Flavio had a question there.
Well, Flavio, I'm not sure I understand maybe there's a typo in your first question, you could rephrase it there, but your second question, what is your point of view on sequential versus Bayesian? So sequential methods can be applied to both frequentist and Bayesian testing methodologies. So it's not either or. In this case, we're applying it to a frequentist methodology. You may be familiar with other testing tools out there that utilize statistical engines that are both Bayesian and sequential. So, I mean, one of the first things you need to know is that Bayesian test methods don't just by nature avoid inflation of false positive errors, but sequential methods can be applied to Bayesian testing.
Okay, and then Ann Saylor whipping out the Scrabble words here. I'm going to let you read that one because I don't even know how to say the word she's saying here. So read Ann's one and see if you can answer that.
Contraindications to using the calculator. How would you address objections from the establishment about the practice of peaking? So I don't know who the establishment would be here, but these methods are not new. They've been around for decades and used successfully in other fields, such as medical research, where oftentimes the trials, the experiments that are being run are scheduled to last much, much longer than the tests that we run. So I don't know that the establishment would have any objections. I think you don't see these methods as much. They are a bit more complex and can be difficult for people to understand and use effectively. Gosh, the regular methods are hard enough for people to use responsibly. So it doesn't surprise me that they're a little more rare, but you know, we hope to change that.
And then Chris K just posted a question. It's a little long, so I might let you just read the question and see if that makes sense to you.
Have you ever compared conversion rate during a test to a pre-test conversion rate? As an additional gut check, how lift of loss is affecting ongoing business results. Right, so if your base conversion rate, compare conversion rate during a test to a pre-test conversion rate. So if I understand you correctly, I think you're saying that, have you ever looked to see if your base conversion rate upon which you sort of set the design of this test is way off from the conversion rate in the control? I think that's what you're asking, versus the other interpretation I might get here is, do you ever do like before after type testing where your test group is a later time period than your control group? So the latter, there are other methods to deal with. The former, I haven't actually spent much time laboring over that type of analysis. I don't think it's absolutely necessary. You could always perform a power analysis on the results that you're seeing, but no, I haven't gone deep into the weeds there.
Okay, so last one, our own Kelly Wortham had posted a question. Can you speak to good ways of coming up with MDE, maybe referencing the runtime calculator?
Yeah, so Search Discovery has another calculator for normal frequentist fixed horizon design, and that does have a handy way of approaching MDE in terms of what you can afford. So if you look at MDE as a parameter of like, well, I'm gonna test for a certain sensitivity, but only if I have the traffic budget to test for that. And I think that's a fine way to go about it. Of course, whatever MDE you choose does not change the actual effect of whatever treatment you're using. And so I think there are also additional perspectives to bring into your MDE estimation. I like to look at like what's actually a meaningful difference in conversion rates over time. So what's something that I would pick up on in my reporting week over week or month over month, what type of conversion volume would that be, what type of difference in conversion rate, and use that as kind of a basis for my MDE. But I've also frequently used the approach of like, well, if I'm going to have to sacrifice on the sensitivity of this test in order to run it within a reasonable amount of time. And of course, the sequential testing calculator can help you deal with that a little better. So if you say like, I'm most likely going to end this test in a couple of weeks, but there may be a chance that it runs out to 6, 12, or 6, 8 weeks. I'm okay with that as long as there's a chance to end early using the sequential method.
Awesome. Okay, well, we have hit our time. We're going to take a look at some of those questions, and if Merritt has time, he's going to try to answer some of them in a Word document as well. But Merritt, thank you so much, and thanks everyone for joining. If you have any super detailed questions, Merritt's contact information has been up on the screen, and we will see you on our next STEC webinar. So thanks again, Merritt.
Thanks, Adam.